Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about curvature, which I wasn't able to get into in the last video. Um, Previously we talked about this idea of arc length, and I kind of rushed it a little bit, but basically this is finding the length of a vector function. So here we're given a curve in space, in 3D space, and we're also given boundaries A and B, and we set up an integral. And from there, yeah, we get its arc length. So here, just to briefly review, we're given a vector function with component functions f, g, and h. This is a continuous curve, so that means their derivative is continuous. Um, and it's bounded by a and b. The parameter t is bounded by a and b. So it goes from a certain t. And here the formula is basically an integral from a to b. And then we get the derivative of each component function. We square that, and then we do a square root. And so to simplify that formula, it's basically the magnitude of our tangent vector, or the magnitude of the vector function, the derivative of the vector function. And so we did a couple of examples with that, like finding the length of the arc. So here we just simply use the formula, plugged in what we have to know, and at the end, we're going to get a real value, a real number. And we also did some examples on how we can use the arc length as a function. So meaning its upper boundary is arbitrary, so it's not permanent. And we also talked about this idea of how we can reparameterize a vector function by changing its, by making t a function of t in terms of s. And we'll only be able to do this using an arc length function. And so we also did an example for that. And now we move on to curvature. So this idea of curvature, so I'm going to write that out. But basically, when we parameterize our vector function, so when we parameterize that, apparently it's called smooth. So this is a smooth on some interval. Let's say I, interval I, if its derivative is continuous. So we've been talking about this all throughout. We can only parameterize, or we can say it's a smooth curve, if and only if its vector function is continuous. And one of the ways it can be continuous, or one of the ways that we can make it continuous, is if we take the derivative and we see that, oh, at every point, well, we have a value, right? So the condition for our vector function to be smooth on some interval is that its derivative or its tangent vector has to be continuous, and its derivative should not also be equal to 0 on that particular interval. So that is interesting. The idea being, actually, I'm not sure why it shouldn't be 0, but basically, if its derivative is 0, then the rate is not changing at all, right? So that's that. So that's the idea. A curve is called smooth if it has a smooth parameterization. So it has no sharp corners or cusp. So basically no holes, no gaps, no, just purely continuous. And so we actually have a definition for this. So if C, so we're gonna say, actually we have a figure here, a visual, just to show that a curve is continuous. So let's quickly show that. So here's the example. So here we can see that, oh, as we continue along the space curve C, well, there are no holes, and there are no gaps, and there are no sharp turns. And so we can determine the derivative at every point here. Why? Because we can draw a tangent vector at each and every point. That's how you know this curve is continuous from this interval A to B, right? See, it's not infinite. The curve has a limit here and here. So those are A and B. So here we're going to say if C is what we call a smooth curve, right? So if it's smooth, and let's say it's defined or described by a vector function, R of t maybe, because that's the notation we've always been using. Recall that the unit tangent vector t has some formula, okay, and indicates the direction of the curve. Oh, okay, okay. So it's defined by this R vector function, and unit vector or unit tangent vector. Okay. Unit tangent vector t, which has actually has a formula here, but so the way to get the unit tangent vector again, so just a little bit of review, is to get the derivative of the vector function and divide it by that tangent vector's magnitude. And this indicates the direction of the curve. So it's not only describing the length, which is 1, which we already know, but since it's a tangent vector, we can also see which direction it's going. So this not only indicates the length, we already know that's 1, but it also tells us the direction of the curve because of its derivative, right? So from that figure that I showed you earlier, you can see that our unit tangent vector changes direction very slowly when C is fairly straight, but it changes more quickly when C bends or twists more sharply. And that makes sense. So here now we talk about a curvature. So the curvature has something to do with direction and how fast our unit tangent vector changes. So the curvature, here we go into a more intuitive definition. So a curvature of, let's say, our space curve C at any given point, so at a given point, is a measure of how quickly the curve changes directly at that point. Is how quickly the curve changes. So here we're talking about how fast that curve changes direction. That's why we talked about our tangent vectors first at that point. And here, to be honest, we don't have to worry about how to get this intuitively because we're given a formula. Um, so to be specific, we define it to be the magnitude of the rate of change of the unit tangent vector with respect to its arc length. So here we're to find the curvature. Well, we need to find the magnitude of the rate of change of the unit vector, the unit tangent vector to be specific, so t, and we need to find the rate of change, so we're taking its derivative, and its magnitude, right? And it has to be with respect to arc length. So it's actually just, so here's the tricky part. If it's with respect to arc length, we're taking its derivative, but it has to be in terms of arc length. So that's the, I don't know why my eraser is kind of funny, but that's the idea. We use arc length so that the definition of curvature will be independent of the parameterization. Okay, because the unit vector has constant length, which is 1, it only changes in direction, contribute to the rate of change of t. And so basically my definition for this one, or the definition of the book rather. Okay, this is definitely definition. Can't spell it. Definition. So we're saying that the curvature of the curve is as follows. So k for curvature, it's like a small k. We get the derivative of its unit tangent vector with respect to s. So here I'm using Leibniz notation, where t is the unit tangent vector. So that's our definition of a curvature. But intuitively, it's how quickly that curve changes direction. So you do realize how, okay, maybe it's not intuitive, but here we're getting the derivative of its unit tangent vector. So we're seeing how fast that tangent vector changes, right? Because tangent vector tells us the direction at that point. If we want to analyze how fast that direction changes, then we want to take the derivative of that tangent vector, which indicates direction. And we do it with respect to its arc length because, well, we're given the arc length. So at least that's my understanding of it. And it's actually easier to compute the curvature if it is expressed in terms of the parameter t instead of s. So yeah, another easier way would be to do it in terms of t, the parameter t instead of s. Which I'm not gonna write it anymore because I cannot understand Leibniz rule for the most part. Oh, okay. Here's an easier one. Oh, okay. Let's actually write this. Yeah. So another easier way would be to, so dt with respect to s or to t. How do we get this in terms of t? Well, this is just dt over ds, which we already have. We multiply it to ds over dt. So this is the arc length function, right? But we take its derivative. This is the derivative of the unit tangent vector with respect to s. And so we multiply that. And the nice thing about this notation is you can cancel this thing. So that's the nice thing about it. And so from there, we can say it's curvature. Don't know why they denote it as k when curvature starts with c. So this is the initial formula, t with derivative of t with respect to s. Well, we can just say it's the derivative of t with respect to dt, or with respect to t, over it's um, over the derivative of the arc length function. And from there, now this is the fun part, or at least for me, I like this better. But ds over dt in my favorite Newton notation is actually just this, right? And that thing which we got earlier is literally the same as the magnitude of my vector function, right? And I think we derived this somehow. Yeah, the arc length function, we are given a vector equation. We derive this thing. And we say it's the arc length function. And so when we take its derivative, we use the fundamental theorem of calculus. And so we get this thing. So it's actually just the magnitude of the derivative of my vector function. And so from here, well, we can say an easier way to do it is through this thing. So we have k of t. So here now, we're making curvature as a function, where we get, okay, our unit tangent vector, we get its derivative, then we get the magnitude over this thing, the magnitude of my r prime. And so let's actually do that. Let's do an example. So here was that example 3. Okay, let me just... Here we're being asked to show that the curvature of a given circle of radius a is 1 over a. So the curvature of a circle of radius a is 1 over a, right? So how do we show this? Well, we need to construct a circle equation, right? And it has to be with radius a. That's what we're being asked to do explicitly. So we can say, oh, we know that a unit circle has a radius 1. But we also know we can say, oh, because we want to parameterize this thing, so we can say this is actually just cosine squared t plus sine squared t equals 1. Now, how do we put the a here? Or we just multiply everything by a. So we can say, okay then, a cosine squared of t plus sine squared of t equals a squared. And we just put an a squared here. Oh, so here's how we get a circle equation with parameter d, right? And what are we being asked to do here? Well, hmm, well, okay. Um, now we want to parameterize this thing. So you want to find a vector equation. That's R of t, right? Because in our formula, we need an R of t. So we can say, okay, if my x squared is cosine squared, my y squared is sine squared. And if I do an a squared, well, then my R of t could just be the vector a cosine t for my x, and then a sine t for my y. Then that's it, because this is in 2D. And now we take its derivative to find the tangent vector. So here we say r prime of t. And then the derivative of this, we assume a is constant. So we have a or minus a sine, because this is a negative sign. I'm just putting the pieces together. So negative a sine t, comma, a cosine t. Okay, what do we also know? Well, now we want to find its magnitude, right? Actually, okay, my bad. Before we even have done all of this, we want to state our givens. So that's usually when we're given a problem, we usually want to state our givens, right? So our given here in this case is that we have a radius r that's equal to a, or no, oh yeah, radius is a, and my curvature, so my k, is equal to 1 over a, right? And so when yeah, okay, so that's done. Now when I take the derivative, I get this. And now I want to find magnitude of r prime of t. And so here I just do this. I do a square root. And then I do yeah, so I basically square root all of them. Then here, what do I get? Well, I get, uh, let me see. I get a squared sine squared plus a squared cosine squared. And then what do I get? I can factor out the a squared. So I can actually factor the a out. And then this one becomes sine squared plus cosine squared, which is 1. So I actually just get a. So here I just get a. Okay. And from there, I can actually now find my t prime of t. or my T of t. So here now we find the tangent or the unit tangent vector. I don't know what the naming was, but it's basically a unit vector that's tangent. So here that's T of t, right? So to find T of t, we need our derivative, which you already have, divided by its length. And so how do we do this? Well, we already have 1 over a, and we multiply it to its derivative here, negative a sine t, a cosine t. And then we just multiply it like so. So if we multiply it, what we get? Negative sine t. I should have added the arrows. So here we get negative sine t. And here we get cosine of t. Right? And so if I take the derivative of this, so I'm just going to put in 2 steps. Because I also need my derivative. And then its length. So here I'm just really getting all the givens. So if I take derivative, I get negative cosine of t. And here I get negative sine of t. And then I get my magnitude. Of my derivative of my unit tangent vector. So I get this thing. So again, I just do a distance formula. So I do this squared. Okay, I'm getting ahead of myself. So I square these, add it to here. And this is just, well, 1, right? And so using what we know, well, we can say that show, well, we say that K of t is this over this. So it's the magnitude of my unit tangent vector over the magnitude of my tangent vector, which is again just 1 over a. And so we proved it. That's the curvature, 1 over a. So the result of example 3 shows that small circles have large curvature. And I agree. Why? Because a circle, you keep on going around, and so it's much faster. The direction that's changing is much faster. And larger circles have small curvature because it takes a longer time to change its direction. But shorter circles, it's really, really easy, right? So that's intuition, right? And here we can see directly from the definition of curvature that the curvature of a straight line is always 0. And that makes sense, right? Because it's never changing if it's a straight line. The curve is it's not curving at all. And although formula 9 can be used in all cases to compute the curvature. Oh, okay. So we have another formula here that apparently is more convenient to apply. So what's kind of funny is they gave us a lot of formulas, but we're apparently going to be doing this one. So that's stupid. Anyway, so apparently there's a more convenient theorem, and this is a theorem. So it means can't be disputed. So here the theorem states that the curvature of some curve or of the curve given by some vector function, let's call it R again, is as follows. So I'm not going to go through the proof, but you guys can go through it. But basically, it's the derivative, and I get the cross product with its second derivative. So here I'm talking about my vector functions. So I get the first and second derivative, get the cross product of both vectors. Then I divide that by the magnitude of my first derivative, and then I cube that thing. So you might be wondering, and I am also wondering, where in the world did he get that formula? Well, there's actually a proof for this, which I'm not going to go over. But yeah, there's some proof on how they were able to do this. But yeah, I'm not going to go through it. Okay, so let's do example 4. So here we're being asked to, again, find the curvature. So we're being asked to find the curvature of the twisted cubic. So it's it's another vector function here. You know what's actually, you know why it's convenient now that I think about it, is because you only need to find one thing. And that is you need, or actually two things. And three things, cross product. But you only need your vector function to be able to do a curvature. So that's what's nice about this problem. You don't need to think about unit tangent vectors, which we did earlier. So that's pretty convenient. Okay, and then here we're given t squared, and t cubed. So that's a twisted cubic at a general point. So we want to find the curvature at some point. It's not, they didn't tell us what the point is. And the curvature at the origin. So here we just compute for what we need. So we need to compute its derivative and its second derivative, right? But ultimately, we're going to use the formula. And so r prime of t. So that's 1, 2t, 3t squared. Done. Its second derivative, so I just compute the derivative again. 0, 2, 60. Done, right? And then now maybe, okay, I need to also compute the magnitude of my first derivative. So this is this thing. And I do a distance formula. So 1 squared, 2t squared, 3t squared. Here I get the distance formula 1 plus 4t squared plus 9t to the fourth. Okay. Now, I do a cross product. So here I compute, so from the formula, this thing, r prime of t I don't even need the magnitude yet. We'll do it step by step. After I get the cross product, then I compute the magnitude. Cross product with its second derivative. Okay, maybe I can do the magnitude. Okay, so let me do one step at a time. Okay, I get I, J, K. R prime of 1, I get 1, 2t, 3t squared, 0 to 64. Oh no, 60. And here I just get a new vector and then get that magnitude. So I take out my I, 2t times 60. So that's 12t squared. I subtract that to 2 times 3t squared. So that's 60 squared. I. Okay, let me put this in another page here. So here. Okay. Then I subtract that to my j. Okay. So I get 60 minus 0, j. I add that again. Okay, that was fast. Then I do for k, I take out my k. I get 2 minus 0, and that's my k. And from here, well, I get 60 squared I minus 60j plus 2k. And in vector form, 60 squared negative 62. Okay. And then from here, I get its magnitude, right? So the magnitude of this thing is just the distance formula of this thing. 60 squared, square that thing. The y component, square that thing. The z component, square that thing. And I get something like, I don't know. No, I get 36. 6 times 6, 36. T to the fourth. Then I add that to 36t squared. Then I add that to 4. And I can actually divide everything by 4. So I got 2, 9t to the fourth plus 9t squared plus 1. And then there we have it. We're being asked to find the curvature. I have everything I need. Well, yeah, I have everything I need. So I just go find curvature. So here, now we can find the curvature of this particular curve described by this vector. And we just plug in some t and then we get. Does that help? Well, as of now, I can't think of any application, but it should help us in some way. I might make stuff on this maybe. So here I'm just rewriting the formula, just so that's clear. Okay, but here I just plug in everything. So the magnitude is just this thing. I divide that by my magnitude of this thing, and I cube that. So that would be 3/2. Yeah. So this thing 1 plus 40. Is it 40? 40 squared. And I add 90 to the fourth, and I make that to the power of 3 over 2. And then that's it. I plug in any t, I get something. So what are we being asked? So that's a general point. So that's it. That's one of them. That's a general point. And at 0, 0, 0. So here again, I just make my t equal to 0, right? Because when t is 0, my curvature, my curvature at t is 0. How do I know? Well, I plugged in the 0 here, I plugged in the 0 here, I plugged in the 0 here. So I know that when I'm at this point, well, my t is 0. And so I don't need to say anything about it. So I just say at t equals 0, I'm at the origin. And so at t0, I'm at k of 0. And that k of 0 is, well, we just plug in 0 to everything here. So here we have 0 plus 0 plus 1 all over 1 plus 0 plus 0, which is just 2. So my curvature is at 2. Okay. So we can also find not only a curvature of a space curve, but also a plane curve. So that one, in my opinion, is easier because we don't have to consider 3 coordinates. Okay, let's do one example of this and we're done for today. Okay. So if it's a plane curve, let's say we have this equation, y equals f of x. Well, we say, oh, we can actually rewrite this as r of x. So here I'm using it as a vector where we have some x value and some y value. So here I say f of x, right? And then when we take that derivative of my vector function, I get 1, and I get f prime of x, right? And then if I do a double derivative, or a second derivative, well, I get 0, and I get f double prime, which makes me basically undefined, right? And so if I do a cross product, so here I'm just basing it off this formula. If I do a cross product of this thing, well, I would basically just get 0, 0, f double prime. Yeah, because I did a cross product here. It's just mental. 0, f double prime of x. Yeah, and this is my, if I just multiply this thing, I get f prime of x minus 0. That's how I get it. And so, to get the magnitude, oh yeah, another thing is getting the magnitude of this thing, right? Of my first derivative. So that's just, again, this square root. 1 squared is just 1, plus this thing squared. Fascinating. It looks like an arc length. And so yeah, by the theorem, well, we get something new here. So if I just take this out, so given a plane curve, so here we're just extrapolating ideas. Given a plane curve, let's say plane curve is y equals f of x. Well, curvature is just in terms of x, right? So that's just f double prime of x all over 1 plus its first derivative. I square that, and I do 3 halves. So that's the formula for the curvature of a plane curve that we can use. So let's do one last example, then we'll call it a day. So example 5. Here we're being asked to find the curvature of a parabola. You know what's funny? They actually introduced the curvature for vector functions first before real valued functions. So my parabola is the typical y equals x squared. So we all know what that looks like. And we want to find it specifically at the origin and at one of the points. Oh, actually at 2 of the points. So here we should see if we draw something, right? 0, 0, maybe 1, 1, 2, 4th. The curvature, as it goes to these points, should be increasing, right? From intuition. So let's just use the formula. Well, we can say, oh, I'm going to use formula. So here we treat y as f of x. And so we get the double derivative, and the first and the second derivative. So we get y prime is 2x. Y double prime is 2. And so we can just use our formula here. So we get k of x to get as general as we can. So the double derivative, that's just 2. Absolute value of 2 is 2. Actually, let's cater it to this thing. So the double derivative all over 1 plus the first derivative, square it. Then put everything to 3 over 2. And so just to plug in values here, this is 1 plus the first derivative squared. So that's 1 plus 4x squared. Raise it to 3 halves. All right, now I find it at points. So I find curvature at the points. At 0, 0, 1, 1, 2 fourths, I believe. Yeah. So my k of 0, plug in the 0, I get 2, 2 over 1. This is just 2 over 1 plus 0. So I get 2. So my curvature is at 2. So here I honestly just need the export. I plug in my 1. I get 2 over 1 plus 4. So 5. So it's actually just 2, 5 to the power of 3 halves. And lastly, I get 2. So my 2 is, well, I got 2, 1 plus 4 times 2 but it's the 2 is squared, so I get 4 times 4, so I get 16. 3 halves. So here I get 2 over 17, 3 halves. And so we can approximate this thing. So we can say, maybe just to see more real values. So I get 0.18. Here I get 0.03. So funny enough, actually, that's so my intuition was wrong, right? Because I thought it would curve a lot more. Actually, it's becoming more straight. So the thing is, as my x goes to infinity, right? Positive or negative infinity, because this works for both. Well, my curvature at that function is actually just approaching 0, right? Because here it starts at 2, then I go 1 point, now it's at 0.18, approximately 0.18, and then as I go on, it gets smaller and smaller until it reaches 0, right? Because as I continue my, if I do a parabola here, if I do a parabola, I start here. Now that's slanted, right? Then I go here, then I go here. And at one moment in time, it's going to be straight, where there's no curves at all. So my curvature is actually just approaching 0. So yeah, that's a fun fact. Okay, that's it for this video. I hope you guys learned, enjoyed, and yeah, I'll see you guys in the next one.